Hey guys, thanks for coming to Notes with me. This is a rapid review on dynamics, and just to catch you up and for the week, what's due by Monday are three things: the translated formula sheet, kinematics review, and this dynamics review. So whereas kinematics was about how things move, dynamics is all about why things move. So cause and effect, equilibrium, why things don't move. Most people think about forces when they think about dynamics, so we'll start there. A force, and I think you know the next words we're going to write, is a push or pull. We say it is applied by one object and experienced by another. That's just any force, any push or pull. But what we're really going to look at is net force. This is that single force that replaces all the other individual forces. We tried to do that stool demo in class where we had two people pulling in different directions, and then we used a rope, and you just look at the single direction that the object ends up moving, regardless of all the different forces acting on it at any time. So let's write down that net force is the single force that could replace all the individual forces acting on an object and produce the same effect. We say that forces add up. As you know, I don't say cancel out. I think the words add up are sufficient. Let's say that F net, right, that's net force, is the sum of all the individual forces. Or we say things like sum of the forces. And we use that later, especially with Atwood machines and various pulley systems. We're going to mention weight here, and again later in gravity, but we'll say that weight is the force of a planet on a mass. A couple more forces to play with. We have friction force is due to a surface, and it's acting parallel, opposing motion. Next up is what we call the normal force, also due to a surface, acting perpendicular. There is a coefficient of friction. Remember, that's mu, and there are no units. And it's specific to two surfaces like rubber and wood have a coefficient of friction. And it just says how sticky the two surfaces are with each other. Let's write down coefficient of friction between two surfaces to say how sticky they are. And we'll go over Newton's third law, equal and opposite action-reaction pairs, and Newton's second law, where acceleration is directly proportional to net force and indirectly proportional to mass. We'll talk about how the sum of the forces equals 0 in equilibrium. We'll mention about how acceleration and force are in the same direction. And we can remember that if the sum of the forces is not 0, then the object is accelerating. Oops, there we go. Okay. Now, might as well make a note here since we've been talking about weight. I've been calling it F of G this whole time, but you'll see lots of texts and other professors and teachers use just a capital W. Friction, I again use subscripts, but sometimes it's seen, let's put them all in here, as an F, normal force, subscript, or just an N. And then the other one is usually applied or prime. There's some, or you just label it out. Like if it's a horse, you would write F of horse or something, just to be specific. But weight is cool because it's one of the few forces we know of that can act without touching. You know, we're talking about applied forces here, like me pushing and pulling this pen, but it's also being acted on by gravity. And that's pretty neat. There's only 2 in this course at this time we're going to talk about. And technically, electricity is off the table. So it's just F of G. Let's write it down anyway. And F of E, right? I'm going to say elect so we don't mix it up. Can act without touching. Those are the only 2, right? Gravitational force, also known as weight, and electrical force. Forces at a distance. Interactions, though. Force fields, nonetheless. All right. Let's keep going. Next up, forces at angles. Okay, so I'm thinking of an example where, let's see, something like this. And I can think of a couple stories to tell with this setup. Maybe I'm in an airplane or vehicle and I have a necklace or a pendant of some kind, you know, holding it by a chain. And as the vehicle accelerates, the chain would kind of make this picture. So it could work for that. Have you ever hung anything or seen anything hung from a car dashboard mirror? That's another interesting way to look at how this setup could happen. AP tests like to connect these to walls. We did a couple examples like that, and then they like cut the rope, and you're usually looking for tension. Anyway, so they'll do this. There's an angle involved here. Let's just say our angle is about 22 degrees, and let's give a mass of 0.1 kilogram just to set it up, make it nice and small. And when it comes to forces, can't do forces without, you guessed it, free body diagrams. Free body diagrams are dots or boxes, and they have relative labeled arrows to represent forces only. Okay. So let's do a free body diagram for this mass here. We'll use a dot, and we've got tension, F of T, and F of G. These are probably not relative. Oh, yeah, maybe they are, because if this was bigger, that's a good question. All right. Now, this would be the free body diagram, and that would be the end of the story. The only other thing you can add near a free body diagram would be a coordinate system, just to claim your direction and plane. When you want to break something into components, you need a whole nother diagram. So here we've got the same thing, but now I'm going to lay on top of it my coordinate system. So I can claim that this is the horizontal component of the tension, and this is the vertical component of the tension. This makes it easier. We got here and here. And so now I can use the components to represent the resultant tension, and I can resolve the forces in both directions. Okay, so when you have this kind of setup, you've got FTY is equal to FT sine theta, which is T sine of 68 in this example. I'll give you a second to look at that. Where does 68 come from? There's lots of ways to do this, right? You could SOHCAHTOA it from scratch each time and play the whole geometry game too. The horizontal component, cos theta, T cos 68. Okay, and you can do a lot with this depending on what they ask. The other and last thing I want to go over is, drum roll, the modified Atwood, right? Mod at W. So we're going to derive the acceleration. We've done this a lot. It was on a bunch of tests. By now, I think almost all of you have mastered this. Let's see it one more time. We've got, if we want the acceleration, we're going to also need the net force, the mass. And where are we going to get that? That's going to be from resolving the forces in each direction. Well, how are we going to know what direction they are? We'll have to make some Freebody diagrams. And how will we know which way it's going? We'll have to add some kind of motion ID, key, arrow, arrowhead. The little caret thing is what I want to say. I don't know what that is. We'll just say motion. So here, now we have a plan. The plan. Let's draw it up. Got a table, pulley, mass 1 and mass 2. Assume frictionless pulley and frictionless table unless otherwise stated. But let's say mu is 0. Or is it 1? No, it'd be 0. Yeah, 0. And let's do the plan. So first thing is, which way is this going to go? Well, we'd have to know if M1 or M2 was bigger. So they would have to tell us. Let's make it move by claiming that M2 is greater than M1. Now we can say it's going to go in this direction. And there are lots of shortcuts to this. There really are. Khan has some good videos for shortcuts, and Cedric knows some too. But this is the way I like to do it. What I do know is that there's one string, and that means there's one tension. Okay, this pulley, the strings here and here have the same tension, and that's going to be key to the whole thing. All right, so check on the motion. Now Freebody diagrams, one for each. Okay, let's do one over here for M1. We've got the weight, F of G. You know what? Let's change it up. Let's use a W here just to get more fluent now that we're at the end of the course here. Let's call this weight 1, and that'll be equal to M1G because it's on Earth. All right, I know who you are. Let's claim it. Earth on Earth. Okay. And here it's also got a normal force from the surface, and I'm going to draw these arrows equal and opposite because this block is not accelerating vertically. That we are going to call N1, if you want to be fancy. No, just N, I guess. It doesn't matter. Okay, and we've also got one more here. And let's call that T. Okay. For M2, we've got the weight. Oops, I should have drawn this longer than, because they straight told me right here. So I'm going to draw this longer than I drew M or W1. So W2 will be M2G, and going up less because I'm expecting it to accelerate downward, right? I would draw this as t. And these t's are the same, and that's going to be handy. So these will add up to 0, and we won't have to worry about them. Each of these situations, we're going to apply Newton's second law, right? So here, oh, let's add that here. Oh, it's right there. Perfect. All right, so on this side, we're looking at M2G. Here's another shortcut I'm using. I know it's going to move down, so I'm going to claim that to be the positive direction down just to make my math easier. So it's going to be M2G minus T on this side, and that's all going to equal MA. So says Newton. All right, let's do the same thing on this side, and we're just going to have just the one force here, and it's going to be moving to the right, so that'll be positive, and we'll have just T is equal to M1A. F equals MA, just like Newton said. All right, there we go. Let's rearrange this for T. T is equal to M2G minus M2A. And now we can bring these guys together. T is right there. And we've got M1A is equal to M2G. Can you guys see this? Sorry. Minus M2A, and we can rearrange and solve for A. Let's see, let's add M2A. See if you can beat me. Keep going. Ah! All right, I ended up with M2G over M1 plus M2. That's the derived acceleration of this modified Atwood system as they've given it to us. Well, thanks for coming to Notes with me. Stay tuned next week for conservation laws. You guys have a good day and good night, and see you around.